Kei te whakaranga mai koe ki ngā pātaka kōrero o Tāmaki Makaurau. You're listening to an Auckland Libraries podcast.
For heritage to have value, for heritage to matter, you have to have a community there that celebrates it and connects to it. At the end of the day, these things, although they're from the past, they're kind of living and they're carried through to the present and then on to the future, hopefully, if we do our jobs right.
Welcome to the Heritage Talks podcast, bringing you the best in family and local history from New Zealand, the Pacific, and beyond. Your heritage now.
Welcome, people. I'm just going to say a few words. Apparently, we're to say a little bit about ourselves, about why it is that I might be speaking to you, and then I will drop into about three main points about the Antarctic Society and this map and the connections with LINZ. So maybe a little bit about myself. Obviously, I'm the president. I have been now for a couple of years. I've been a New Zealand Antarctic Society councillor since about 2010 and a member since 2002. I've made two trips to the ice. The latest was in 2012 when I went down there as a volunteer painter as part of the volunteer scheme that's shared between, or not shared, but a partnership between Antarctica New Zealand and the Antarctic Society when room and places allow, and also when there's work to be done down at Scott Base. And so that was for about 5 weeks at Scott Base, and we were scraping windows and repainting windows. So that's a little bit about me. My day job, effectively, I'm in the construction sector. I'm a designer, project manager and associate professor in architecture and construction at Unitec. And I'm also an ex officio trustee of Antarctic Heritage Trust. So I think it's enough about me. The next point is about the Antarctic Society and LINZ, which is a land information organisation in New Zealand. And this was a partnership that was arranged and organised by and large between several people within the society, and one of whom is unable to be with us this evening other than perhaps by dialing in, and that's Nicholas O'Flaherty, who's our editor, who did a huge amount of work with LINZ. And the whole purpose of this new map, the 2020 map, was to celebrate 60 years of the Antarctic Treaty, which was signed in 1959. This map has actually worked together with the latest magazine, which is a bumper version that went out in February. It's gone to 2,700 schools, all the schools in New Zealand, in other words, whether primary or secondary. And it's also gone out, of course, to our full membership. And that was largely as a result of sponsorship by various science agencies, NIWA being one of them. Thank you, Natalie. And also through GNS, and then also through NZ Sea Life. And most of the universities also put up quite large sums of money to sponsor the fact that we could actually get these maps and magazines out to all of the schools. The third point I want to make is join the society and get the map and the double issue magazine from February 2020. It will only cost you, if it's an individual, about $75. So what you need to do is go to the website, which is antarcticsociety.org, .nz, and choose membership. And once you get to there, join us now. Or you can email membership@antarcticsociety, or one word, .org.nz. That's me. And I would now like to introduce Dr. Robin Falconer.
Hello, I'm Robin Falconer, and today I'm going to talk about some of the series of maps of Antarctica that have been produced over the last 70 years or so. I'm retired now. I first went to Antarctica 55 years ago. I went down on the New Zealand Navy ship Endeavour, which was taking supplies down to Scott Base and McMurdo Sound, and we were mapping the seafloor. And I've had 8 trips to Antarctica on ships, mapping the seafloor, and I did a PhD on the tectonics of the area, how New Zealand, Australia and Antarctica have separated over the last 100 million years, and then spent most of the rest of my life in marine sciences and universities, research organisations, and in industry. So I've been making maps basically all my life. Now, Lands and Survey, or the original government department and now called LINZ, Land Information New Zealand, also makes maps. That's what their core business is. And they make all sorts of different ones of New Zealand property and different types of things. But tonight we're talking about their Antarctic maps. The first one they made was in 1952. On the screen now we're looking at the 1955 one. The 1950, it's not much different than the 1952 one. And that was the first official government map of showing Antarctica. And now we're looking at the 1955 map, and it's fairly early. It's got some place names, mostly around the coast, because that was what was known about then. There are still some areas on this map that are completely unknown on the right-hand side and some of the left-hand side. There are places where the coastline is dotted because nobody had ever flown over it, no ship had ever been there, and we just simply didn't know the shape of the land at that time. So interesting, there were still unknown areas in 1955. There aren't any names of bases on this map. The one that's most familiar to us as New Zealand is the Scott Base. It wasn't there then, so it's not on this map. But the interesting thing is, why did these maps start to appear? In 1952, there was interest developing in Antarctica after the Second World War and the long period of nothing happening since the expeditions of Scott and Shackleton and others. But 1955, the world was getting ready for the International Geophysical Year, which was a huge international science program that was done in 1956-57. And it led to a huge number of nations establishing bases in Antarctica, including New Zealand establishing Scott Base starting in 1956. And living just near me and Mike and I is Randall Hickey, who was actually the leader of the building of Scott Base in 1956, and he's 93 and he's still going strong and he still talks about it whenever you meet him. So now we'll go over, Natalie will take us over to the next map, which is 1963, which is after the IGY. You can see a lot more detail. The huge amount of activity in the International Geophysical Year led to much better knowledge of New Zealand. And this map actually contains the locations of lots of bases in Antarctica. There were over 30 bases established in the IGY period. And for the first time ever on a New Zealand map, we see Scott Base, and Scott Base is in the middle there. And we'll see that in a little bit more detail on some of the other maps. There's a little bit of detail on the interior. The light blue area, well, the light blue areas where it was thought from the results of IGY that the land was below the sea level, and the pink areas where it's above sea level. And that was mostly stuff that was learned by people traversing over the ice and doing science measurements. There are lots of names of different sectors around the coast that have been named. Then after 1963 map, Lands and Survey produced maps in 1979, 1980, and 1987. These progressively add a little bit, but they're not enormous changes. One of them showed sea ice extent and mostly a few extra details. But the next one we go to is 1994 that Natalie will put up. And so this is quite a different looking one. It's showing the bases again, but if one looked carefully, the interesting thing here is it's showing the heights of the ice and the land in the interior. We hadn't seen that on any of the earlier maps. There's also a little insert up in the corner which is the area around Ross Island that shows Scott Base and McMurdo Sound. They're just at the bottom of the map in the red there. And that's Mount Erebus, the active volcano that Scott Base sits and McMurdo Base sit just nearby to. Then there's a whole gap of 25 years before the next map. And the next map shows what happened after 25 years. And that's the one we're talking about, 2020, that Natalie will pop up now. And this is the map that we've just produced. And it looks quite different than the other ones. For me, as an ocean scientist, it's kind of exciting. It's showing something in the oceans for the first time. And there's some relief shading that gives you an idea of the shape of the seafloor. There's some interesting relief shading on land. There's some detail of big overland traverses. All the bases are there. And also what we've done now in this map is we show some little insets of science in different subject areas around Antarctica. So now I'll hand over to Natalie to tell you about some of the science of Antarctica, since we now have the modern map. Natalie.
So just to introduce myself briefly, I am a physical oceanographer or marine physicist with NIWA, our National Institute for Water and Atmospheric Research in New Zealand. But I've also been a member of the New Zealand Antarctic Society, I think, since 2003, which was the year that I first went to Antarctica as a master's student. So I've since been 6 times in total, and I'll just give you a little bit of a flavour of the science that I do, so that you can see how my presentation is going to be a little bit biased. So I consider that I work at the intersection between these sort of 3 components of our climate system. Antarctica is where my work is based, but I work in the ocean that's immediately adjacent and work to understand how what's happening in the coastal regions of Antarctica potentially can have knock-on effects for the rest of the global ocean. And of course, we can't talk about Antarctica without talking about climate change too. So you'll find me in the middle of that Venn diagram. So I've gone back to sort of basics here because I realised that with the web streaming, we now potentially have a bit of a broader audience than might have actually turned up to the library in Auckland. So I don't really know what people know, so excuse me if I'm teaching you to suck eggs. So in Antarctica, there's basically 2 main types of ice. On the left, you can see what's called sea ice, and this is frozen ocean. So the atmosphere around Antarctica gets sufficiently cold every year, every winter, that the surface of the ocean will actually freeze. And it freezes to between 1 and 2 meters thick. It's obviously thicker as you get further south and closer to the continent itself. It's so much of the ocean is frozen, this top sort of surface, this like blanket over the top of the ocean, that it effectively doubles the size of Antarctica every winter. And it provides a substrate and a habitat and protection for the ecosystem of the Southern Ocean. And then we move to the other main type of ice in Antarctica. So this is the ice sheet or grounded ice, which begins life as snowfall into the centre of the continent or onto the continent. And as that snow builds up, it under its own weight will turn into ice. In places it's up to 4 kilometres thick, and in fact it's so heavy, might not surprise you, but it's depressing the bedrock. And there's approximately 60 metres of sea level equivalent, global sea level equivalent, wrapped up as fresh ice on Antarctica. So this is me, obviously. And where we're looking now is sort of directly south, down towards the South Pole. To give you an idea of where we are, this is Scott Base, circled in red. So this is on the hill overlooking Scott Base. And I wanted to draw your attention to this feature. So hopefully you can see those red lines. Above that, what you're looking at is ice shelf. So this is the floating extension of those land-based glaciers. So this is fresh ice that began as snowfall. And then towards the front of the image is sea ice. So if I just take that line away again, you can see it clearly from this vantage point. In fact, if you're right down there on the ice itself, it's not that easy to see if the light is not right. And it's only a step change of about 2 meters in this location. The light is right in this case because we're getting low light to give us shadow. So I do a bit of outreach, and I thought I'd just play this little video which gives kind of an overview of my science. So here we are on the flight down, and that is right at the edge of Antarctica. Some views of the sea ice, and then here we are landing on the ice. In terms of the work that I do, I typically will take out a set of shipping containers. Here they are being dragged by the bulldozers out onto the sea ice, where they'll be set up as a container camp. There we have accommodation, science labs, we've got a generator to run everything. And then it's time to actually start the work. So I work in the sea ice immediately in front of the ice shelf. So the ocean connects these two. So it's much easier to get through just 2 meters of sea ice. But because we're so close to the ice shelf, the stuff that I'm scooping out now is called platelet ice. And it only forms when you're that close to an ice shelf. Here we are deploying this sort of fundamental instrument for oceanography. It measures temperature and conductivity at every depth. And so in this case, we send it down and back up again 3 times over. And here we've got 400 meters beneath our feet. And then this is actually what the environment that I'm surveying looks like. I don't get into the water myself, but it's some pretty neat imagery that we've been able to get lately. And as I said, I do quite a bit of outreach, taking Antarctic science into schools. I find, of course, that Antarctica is quite easy to get people to engage with, and it's kind of a way into science to hopefully get some kids inspired. So I was pretty excited when this new map came out and the initiative was taken to get in all of this sponsorship. You'll see I've highlighted all the various institutions there who've contributed to this work in order to produce that large number of both the bumper issue of the map and of the magazine and the map itself, and get it out to every school in the country. So kind of my involvement here is as a scientist who's keen to make the most use of this outreach tool. So for the purposes of this map, for this talk, I just thought maybe the best thing to do would just be to go through the various elements that you can see on the map itself and how that relates to Antarctic science in general. So of course there's the inset at the bottom, similar to that 94 map where we've got the the zoom in of Ross Island, which is where both Scott Base and McMurdo Station are. And of course, this is New Zealand's backyard and was also the jumping off point for many of those original surveys into Antarctica. Just to point out that that photo on the left is taken where that circle is and looking off towards the south over both the sea ice first and then the ice shelf behind it. So if we look at the main component of the map, the central map there, in terms of the features we can see, here you see a continent that is surrounded by ocean, excuse me. And this is exactly the opposite to the situation in the Arctic, which is of course an ocean basin surrounded by land, which makes all the difference in terms of how Antarctica affects our climate. You can see dotted in red the Antarctic Circle, and that is of course where you will for at least one day get 24 hours of sunlight in the summer and 24 hours of nighttime in the winter. So as you go further south, of course, you end up with a longer period of complete sunlight in the summer and a longer period of complete darkness in the winter. We've also got marked on this map the various traverse routes that have been taken and their national scientific bases. So we've got, there's 31 marked across the main continent itself, and then a further 34 of them on the Antarctic Peninsula. The peninsula itself recently experienced, you might have noticed in the news, a record high of about 18 degrees, and that was, you know, that's pretty hard for me to understand. I've never been above zero in Antarctica before. And then we move on to the features of the continent itself. So the Antarctic ice sheet is made up of three component ice sheets. Here you've got the East Antarctic ice sheet, which is the main body of the ice sheet. It's up to 4 kilometres thick in places, as I said earlier. And if that were all to melt and end up in the ocean, that would be about 53 metres of sea level equivalent. Then we have the West Antarctic ice sheet. It's much smaller, only 3 metres of global sea level, but at the moment it certainly looks like it's considerably less stable than the East Antarctic ice sheet. So that could mean significant sea level rise in a relatively short time frame. And then the third part, the peninsula, just a relatively small part of the Antarctic ice sheet, but it is rapidly changing. We also have shown here the contours of the ice elevation, as was in the 94 map as well. I think these are probably considerably updated since then. And we've also got distinction between the types of glacial ice. So there's the land-based ice, which is grounded on the land, and then these extensions out over the ocean, the floating sections of the glacial ice sheet, which are called ice shelves. So the role of these ice shelves, they play a critical role in terms of determining the speed at which the ice sheet leaves the continent and enters the ocean. They effectively form a sort of a plug, or they have this buttressing effect that holds back the land-based ice. So the way that they behave will determine, or is determining, the rate of sea level rise contribution from Antarctica at present. And it's now been established that the ice shelves respond most to the ocean interactions that are happening underneath them, which of course is quite difficult to monitor, because in order to do that you actually have to get in under the ice shelf itself. There's very little information that can be gained from the ocean interactions from the surface. So in the case of the Ross Ice Shelf, if you were wanting to get through there and collect some ocean data, you'd need to be getting through between 300 and 700 meters of ice first before you got into the ocean underneath. And that has been done a handful of times, but in that case it's a pretty large piece of ocean that has very few data points. So every single data point we have is very helpful in terms of understanding what's happening. You may have noticed originally that I called my talk the layers of Antarctica. So starting with this top layer, the ice that's sitting on top of the continent, it in itself is layered. Here's a nice image from NOAA of an ice core. Of course, as the snow falls year after year and builds up and then becomes the ice, you're left with this stratigraphy, a record going back in time of the climate. So not me, but people I work with have been collecting data from these ice cores. And so here, as you go down through the ice and you collect your record of carbon dioxide, this is actually, as the ice closes over, you're left with a sample of the atmosphere at the time that it closed over. So the actual carbon dioxide component of the atmosphere at that time. And then there's another way that this same sort of information can be collected in terms of the temperature. So you can see from a single ice core going back 800,000 years, we can see the in-step behaviour between the carbon dioxide and the temperature. Going back to the further features of this main map, we can also see the major ice streams identified, they're labelled there. The features that have a surface expression, remembering that we're under a lot of ice, so if there's a surface expression, it must be a fairly major feature, particularly items like the Transantarctic mountains there. And as Robin alluded to before, we've got the seabed bathymetry indicated. You can see the difference between the light blue, which is the continental shelf, and going off into the deeper abyssal ocean in the darker blue and grey shades. And then also Lake Vostok is highlighted there. So that's just one example of the subglacial hydrology that's going on. So I'm going to insert a layer that's not shown there, just to give you an idea there. If we were to take the lid of ice off Antarctica, we would reveal this intricate network of about 300 lakes that are then interconnected so that liquid water is flowing between the lakes, sustained by a geothermal heat flux coming from underneath in combination with the pressure of the overlying ice. And these are interconnected so that one of these lakes might drain into the next one down the line. And then I'm now going to go to each of those 4 smaller maps that are in the 4 corners of the main map. And so we have the bedrock elevation and also the seafloor bathymetry. So in this case, there's been a long history of aerial radar surveys, many decades long, showing both, revealing both the thickness of the ice sheet and the topography of the bedrock underneath it. Two main methods are used from the satellites. Gravimetry, where it's possible to effectively weigh the continent by assessing the very fine changes in gravitational attraction, and that combined with laser altimetry, so this is basically sending a laser beam and seeing how long it takes to come back, you can identify where the surface is. So by combining those two measures, you can effectively work out how much ice must be sitting on the top, and therefore how much, what the elevation of the bedrock is underneath. And in particular, this reveals how much of the West Antarctic ice sheet is actually grounded on bedrock that is below sea level. So this puts it at, makes it quite vulnerable to any changes in ocean conditions and ocean temperature. In the last just handful of years, the US Antarctic program have been conducting Operation Ice Bridge, which aims to collect a whole heap of data to inform maps like these in high resolution. And it's basically a plane kitted out with all these different devices to simultaneously collect all these different types of data. And as we go off the continent itself and into the ocean, well, now you can't collect bathymetry data remotely, well, from the air or from satellites, sorry. You have to be there with a ship. So here's a nice graphic from the British Antarctic Survey showing how an instrument sitting on the base of the ship will send out a sonar and acoustic signal and in a wide swath, so that it's getting information on the seabed bathymetry in sort of a long stripe, and you come back and collect it in the next stripe and add all these together. So NIWA itself does work. Here's our ship, the Tangaroa, coming into the Ross Sea to do this sort of work as well. Moving on to the next of these small maps, we have the map of the ice velocity. So the slower moving parts are in the darker blue shades, and those correspond with the locations of the domes. So these are the places where there's a local rise in the elevation of the ice sheet, and the ice basically flows away in every direction from each of these domes. So that's where the ice isn't moving, or barely moving at all. Whereas if we come down to the red colours closer to the coast, and especially the fronts of those ice shelves, this is when the ice is really speeding up. And in particular, that area of West Antarctica, which we noted was largely grounded on bedrock that's below sea level, this is where the ice is really speeding up as we speak. What's the implication of that? Well, if we look at current levels of sea level rise, I've put the glass there on the side to remind you that this is now ice that we're taking from the continent and putting it into the ocean. So if you were doing that in your whiskey glass, taking ice and putting it in, the level of the liquid will come up. So at the moment, sea levels are rising and about a third of the current rate comes from mountain glaciers. So about a third is coming from thermal expansion of the ocean. So as the ocean itself warms up, it takes up a little bit more space, but when you spread that over the 4 kilometres or so that the ocean averages, that adds up. And then about a third of current sea level rise is coming from melting of the polar ice. Well, the thing is that those first two have a sort of natural limitation, but there kind of isn't really a known limit on how much polar ice will melt on our current scenario. There's a lot of unknowns, so that's kind of where the big uncertainty lies at the moment. Moving on to the third of these smaller maps, we've got a map of sea ice extent. Of course, the map is stationary, so it's showing in the 2 shades of orange, you've got the maximum winter extent, so that happens in September, and this is an average extent over that long period, so 30 years. And then the darker orange is showing you the summer minimum, which happens in February. And if you look at the animation, you can just sort of see 1 year of that happening over the continent, and you can see what a massive change it is when you consider that Antarctica itself is about the same size as North America. So we're changing the nature of, so this natural process, this sea ice formation, changes an area of the ocean that's about that again, from dark ocean to bright white. And the sea ice itself has multiple layers. If you look in the top part of the sea ice itself, there is labelled as granular ice. That's just the very first starting phase of sea ice. And as soon as that forms, you can start to catch snow on the top. But you can also start forming columnar ice underneath. This is where the ice crystals align, and you start getting extension of that crystal growth down towards the ocean. In most places around Antarctica, that's all you would get. But this last bottom bit, that's kind of my specialty. That's where I work. So close to the ice shelves, you get these other types of ice that contribute to this layering system within the sea ice itself. The sea ice obviously changes how the atmosphere and ocean interact. You're sticking a fairly substantial barrier in between them, so it controls on a seasonal basis how the heat and nutrients are exchanged. And as I said before, it provides a habitat and protection for the vast ecosystem of the Southern Ocean. It also, as I said, changed the surface of the ocean from dark blue or almost black colour to a bright white, and it's even brighter when it's covered with snow. So where you have these dark patches, that's where the heat from the sun can be absorbed into the ocean. But once it's covered with sea ice, that energy now gets reflected back out to space. So you can see it has quite a role in controlling the heat balance that comes into the climate system itself. Sea ice is formed from ocean water, which of course has salt in it, but the salt can't be retained within the ice structure itself. So what we end up with was is relatively almost fresh ice sitting on the surface of the ocean, but that salt has to go somewhere. So it's cold, and you end up with this cold, salty water, which is much denser than the surrounding water, and it wants to drop straight to the ocean floor. So here's a nice little animation showing that deep water getting formed on the continental shelf. I'll get it started. Getting on the continental shelf, and then it's rolling down into the deep abyssal ocean around the continent. And that changes on a seasonal basis. So we sort of end up with this pump, if you like, happening in the ocean. So close to Antarctica, the sea ice forms and you get this release of dense salty water, which then is one end of what's called the global ocean conveyor belt. And this is a large scale overturning of ocean water, and this controls to a large extent how heat is distributed around the globe. Also on the right there, I think it's 20 years of sea ice extent, perhaps longer than that, can't remember now. And you can see I've plotted it on an oscilloscope like a heartbeat, because it sort of plays the role of a heartbeat in the ocean, the same as our blood circulation in our bodies. We get flow along key circulatory paths. This ocean flow delivers oxygen and nutrients to the deep ocean, and as I say, regulates the temperature of the ocean and the climate in general. But if we just look at the maximum extent, so this is the September extent of the sea ice itself, over about 40 years of satellite observations, there was this gradual trend to slightly more and more sea ice coverage, and that has rapidly dropped off in the last couple of years. It's not really clear whether that's sort of a new step change into a new regime, but the point of this graphic is that that total change that happened in just those last 3 years is equivalent to about 10% of the total signal. So that's quite a change if you're thinking about your own heartbeat. If you were to get that sort of signal change, would be sending you into the ICU. So perhaps we need to do the same for our planet. So the work that I do, this is kind of getting much closer to home now. The ocean gets underneath the ice shelf and can start to melt off the base of the ice sheet. And then that fresher water comes out to where I can observe it from the sea ice in front of the ice shelf. And on the way, it creates ice crystals in the water which grow bigger and bigger. So by the time it comes out from underneath the ice shelf at the front to where we are on the sea ice, you've got quite a large number of ice crystals that all want to grow and get bigger. And as they get bigger, they have a tendency to float up, where they will land at the base of the sea ice. And so if you're down in the ocean, which I'm not, but we put our instruments and cameras down, this is what you would see looking back up towards the surface. So you've got this lovely blue colour, which is being filtered by snow, and then sea ice, and then this thick layer of crystals. In this case, there's about 4 meters of these crystals sitting underneath the ice. And you can also see that there's kind of this rippled pattern or bumps along the base. You can kind of think of the process to ripples on the sea floor, except it's depositing at the upper at the top of the ocean underneath the base of the sea ice. And the different colours there, where it's darker and sort of greeny colour, that's where it's colonising algae inside that platelet layer. Another image of that, which I quite enjoy, here you've got much darker greens, so much more algae in this location, and quite a clear comparison with the blue light beyond that's completely algae free. You can also see our resident seal Walter from 2018, and here he is occupying one of our science holes. So the way we set up our field camp, one or more of those containers has a hole in the seafloor, so we can lift the hole in the floor of the container, so we can lift that hole out, melt our way through the sea ice, and then we've got access to the ocean from inside the shipping container. Well, of course, this is convenient for the wildlife, because if we weren't there, this seal would have to be maintaining his own hole in the sea ice in order to breathe. So of course, he's able to breathe without risking his teeth. Not only that, but we blow warm air down onto the surface in order to keep the surface open. So the seal, who's never breathed air above 0 degrees before, now finds a face full of lovely warm air, and it was actually quite a pain because he would jam himself against the sides of the hole and go to sleep with his face underneath the flow of warm air, which meant we couldn't do anything. But the aim is to get instruments down into the ocean underneath, but we're working in water that's so cold, it's actually below its own freezing temperature. So anything that you put in there instantly becomes a site where ice will accumulate, including ropes and instruments. That instrument, I'll just click ahead. If you look at the image on the right there, that's 3 days worth of deployment. So in less than 3 days, the instrument became completely swamped with ice and not collecting any useful data. And here's a little time lapse of what it takes to bring up those instruments. And as they're coming up, you can see the hole in the sea ice is getting filled more and more with these ice crystals. We have to clean off those instruments. So they're now ready to go back in, but there's so much ice now in the hole that we can't physically put them back in again. There's more instruments to bring up, so they also have to be cleaned. And of course, there's ice coming off not just the instruments, but the rope in between itself. So now another whole process of cleaning all that ice out. So here we've got a pump that's sucking the ice and delivering it out to the outside so that we can actually start to see the ocean again. So after quite a bit of work, you can see the ocean there again, ready to receive our instruments. Okay, and the last corner of the map shows the Southern Ocean, and in this case you can actually see the location of New Zealand in the north of this segment. So as I said earlier, here we have a continent that's completely surrounded by ocean, which is the opposite situation to the Arctic. And this is critical. When the Drake Passage opened between 17 and 49 million years ago, that then allowed the ocean to circulate the continent unhindered, which effectively isolated the continent from the rest of, contained the continent within its own current, and that current is called the Antarctic Circumpolar Current, which circulates in a clockwise direction. And just comparing that, the flow in that current, don't worry about the units here, just look at the relative values. So we use the term sphere drup to measure the rate of flow in that current. So the Antarctic circumpolar current sits between 120 and 150. If you compare that to the Gulf Stream, which is the other major ocean current, the next major ocean current, well, that also gets up to 150, but it starts at only 30, which is still an awful lot of water, I'll say. If we look at the Amazon River, that's only 0.2. And if you combined all the rivers in the whole world, that would come to about 1. So the Antarctic circumpolar current sits between 100 and 150 times all the flow of all the rivers in all the world. And the ocean itself has layers. Here's a rather simplified, but it actually still looks quite complicated, doesn't it? Schematic of that layering system. You can see we've got the red layer at the top, then going down through the yellow, green and blue layers. And these represent various different processes that are happening and how that water is being distributed into the ocean basins and from there around the globe. But you can still get layers even below the ocean water itself. So actually my first visit to Antarctica was under this program, the Antarctic drilling program called ANDRIL, whose aim was to sit at the front of the Ross Ice Shelf and collect a sedimentary record from beneath the ocean. If you have a time when there's completely open water, you'll get one sort of sediment, whereas if you move to a really cold period and the ice has completely grounded in this location, then you'll get a completely different type of sediment deposited. So you can see that if you were to collect a long core like this through all these layers, then you can again go back in time, similar to those ice core records, but now you're getting a much longer record. And so here's on the right is an actual photo from that effort, and you can see very clearly those different types of sedimentary layers that have been left, and I'm not really the one to tell you about what that record means. But those, as we said earlier, those ice shelves which control the rate of flow of the Antarctic ice sheet are responding mostly to the ocean that's circulating underneath them. So if we think about the global ocean, it's actually at present has absorbed 93% of the additional heat that has gone into the climate system as a result of anthropogenic or human activities. And only 1% of that heat has gone into the atmosphere, which is actually what we experience in terms of experience of climate change. So if you think about all that heat, if it had gone into the atmosphere instead, it would already be 50 degrees warmer and too warm for human habitation. So in effect, the oceans have saved us from ourselves for now, but it also means that we've committed to a longer term change, and that change is coming to Antarctica now. And I think just to finish, I wanted to show you this video from some New Zealand work that happened on the Ross Ice Shelf. A team from New Zealand and other countries around the world have drilled through the ice shelf, 300 metres of ice shelf at this site to get into the ocean below. And then, of course, putting the ocean instruments down into there to collect these very precious data that are very hard to obtain. So looking down through that borehole, you can see that it's quite otherworldly. And this is literally a location that has only been, so the Ross Ice Shelf is of an equivalent size to France, and it has they've only been data collected from it, from the ocean beneath it, about 5 times in 5 locations. And the last thing I just wanted to say was that this work in Antarctica, understanding the Antarctic oceans underneath the ice, is also helping to prepare for work to understand icy worlds in our solar system. So this is Europa, one of Jupiter's moons, and it has the same sort of idea as Enceladus, which is Saturn's moon, because in both cases you've got this global ocean that covers the entire world, and that's topped by an icy crust. So the Antarctic ice shelves, where you need to get through a thick layer of ice to get into the ocean underneath, are Earth's analogues for these icy worlds. So that's all I have for you. I hope you've enjoyed that, and I hope there was something there that piqued your interest.
You've been listening to an Auckland Libraries podcast. Stay tuned for more Heritage Talks. You can find further information on our page at SoundCloud or see the Auckland Libraries website.